This lesson covers kinetic molecular theory. The interesting thing about this unit is that it's really the first time that we haven't talked about the theory first and then applied the math. For the most part in this unit, we've talked about all of the math in the first three videos in this unit, and now we're going to talk about the theory. And I think what you're going to see is now that you have a really deep understanding of the math, the theory is just going to flow from that sort of quantitative method or understanding of the information. And we're going to try to understand the kinetic molecular theory through the following objective, which says the student will be able to describe the postulates of kinetic molecular theory and apply these postulates to contrast properties of gases in ideal versus real conditions. I've talked about multiple times what the kinetic molecular theory is. For example, in the first, or rather the second video when we talked about ideal gases, I told you that ideal gases subscribe to all five postulates of the kinetic molecular theory. And our purpose by the end of this video is to be able to understand what all five of those postulates say and how they can be applied to gases. So these are the five postulates of kinetic molecular theory. The first one says that all gas molecules are considered to be point masses. What that means, and I want to define what a point mass is. A point mass is a substance whose mass is very nearly zero, and that is to say that it is negligible. So that's what I call the mass postulate of the kinetic molecular theory. The important part of this is that it means that gas molecules, their mass is so very nearly zero that if they're placed together, there is no void of space in between those molecules. We know that if I put two molecules together, their sort of energies can overlap, or they can also cancel each other out so that there's a void of space in between there. Well, a point mass means that there is no space in between there because the mass is very nearly zero. The second postulate says that the average kinetic energy of any gas is a function of its absolute temperature. I call this the energy postulate of the kinetic molecular theory. And the important part here is to understand that if I have two gases at if I have two gases at one temperature, that their average kinetic energy is going to be the same, because the average kinetic energy is a function of the absolute temperature. The equation for kinetic energy, or even the average kinetic energy, is 1/2 mass times the volume squared. And this makes sense. I know that if I have a certain mass of a substance, then I can calculate its volume, or rather its velocity, if I understand its kinetic energy. The third one says that gas particles move in rapid, random, straight line motion, and I think this is one that you guys can understand intuitively. You know that gases have the most energy out of all the three states of matter, and that they move at the fastest rate because they have a higher degree of disorder or randomness. That is what I call the motion postulate of the kinetic molecular theory. Fourth one says that the volume of the gas molecules are negligible compared to the volume in which they are contained. And what I like to describe in this postulate, the fourth postulate, is imagine that you're in, let's say, your bedroom or a classroom, and we wanted to figure out what the mass of that entire room is. It's, although a laborious process, a pretty easy process. All I have to do is add up all the individual masses of all the substances in the room, and I would, for the most part, have the mass of the entire room. I think we can all agree on that. The analogy that I want to impart to you here is that there was no part of the equation had you weigh the mass of the air in the room. You didn't go by and calculate each of the individual gas molecules or air molecules in the room. And I think the fourth postulate of kinetic molecular theory is able to answer that. It's because the gas molecules, the volume of those gas molecules are negligible compared to the room that you're in. So you can just say, yeah, I know that the gas molecules are going to have a very small part of the mass in the room, but it's negligible, and I'm not going to count them. That's what I call the volume postulate of the kinetic molecular theory. And finally, the attractive and repulsive forces between gas molecules are negligible. That's to say that if I have one gas molecule A close to another gas molecule B, that those attractive and repulsive forces are can't really be accounted for. That's the fifth, or I call collisions. That's the collision postulate of kinetic molecular theory. So now we've talked about the five postulates of the kinetic molecular theory. Now we need to talk about how gases can deviate from ideal behavior. We discussed ideal gases a couple of lessons ago when we used our calculations, but we didn't really discuss what an ideal gas is. So what I want to do here on this slide is I want to discuss what are ideal gases, what two major assumptions we make about those ideal gases, what happens in reality, so we'll juxtapose reality versus ideality, and then we'll talk about why. Why do these changes happen, and let's explain what really happens to gases when they can deviate from ideal behavior. So gases have two defining characteristics when we talk about ideal gases. And the first one is that the gas molecules themselves occupy no appreciable volume. And we saw this in the fourth postulate, or the volume postulate, on the previous slide. The second defining characteristic is that gas molecules have no attraction or repulsion for each other. This is in number 5 when we talked about the collision postulate of the kinetic molecular theory. The problem with these two is that they are major assumptions. They work really well for us when we talk about ideal gases and we want to incorporate those into the ideal gas equation. But you should know that this is not actual reality. And in fact, ideal gases don't really exist. We can talk about when gases behave in ideal conditions, but for the most part, there are no ideal gases that we can just find all the time, always, in every situation. So that moves us into the next portion of this, and what really happens? The answer to that question is not really a simple one, but what we're going to do is we're going to pare down that understanding by saying that gases deviate most from ideality at high pressure and low temperature. And what I want to do in this understanding is I want to explain why. What's happening at high pressure and at low temperature conditions that allow gases to deviate from ideality. So let's start off first with the high pressure. So gases are going to deviate from high pressure in that the main factor is due to the particle size or the molecular weight. There's a very specific reason for this, and that is as the pressure increases and the volume decreases, remember that relationship, the volume of the gas molecules becomes significant in relation to the volume of the container. So you can imagine that if something has a high molecular weight, it's going to deviate more from ideality than something that has a low molecular weight because of that relationship between that volume decreasing. So again, as that pressure increases, the volume is going to decrease, meaning that the volume of the gas becomes significant in relationship to the volume of the container. So that's an explanation of our high pressure argument. The next portion is the low temperature argument, and the main factor for the low temperature is due to the presence of intermolecular attractive forces. So that's us talking about the low temperature here. Let's talk about why. If the substance were at high temperature, so let's think about at ideal conditions. If the substance were at high temperature, the kinetic energy of the molecules can overcome the attractive influence and the gas behaves ideally. But we're not at high temperature, we're at low temperature. So at low temperature, the energy is such that the substance can not overcome the attractive forces. So the stronger the intermolecular force, the more attraction exists between molecules and the more the gas deviates from ideality. So in summary, if I'm talking about low temperature, the stronger my intermolecular force, so if we're talking about a covalent compound here, hydrogen bonding, which is a subset of dipole-dipole attractions, has the strongest force attraction. So hydrogen bonding has the strongest intermolecular force. So therefore, at low temperature, it's going to deviate more from ideality. Let's take a look at an example on our practice test. The question says, which of the following conditions would cause a gas to deviate most from ideal behavior? Well, I have to think about what are those two conditions. So I'm looking for the answer here that has the highest pressure and the lowest temperature. So I have to ask myself, of course in a multiple choice problem, which one can I immediately get rid of first? Well, as I said before, the first one that I can take out is STP conditions. Remember, STP conditions are when gases are going to behave most like ideal gases. So I can take B out immediately. If I take a look at high pressure and low temperature, then the next one that I can take out is answer choice D, because this guy so happens to be at a high temperature. This is a high temperature and a low pressure. Remember that standard temperature and pressure is 760 millimeters of mercury. So this gas isn't even at standard temperature, it's below standard temperature, or rather standard pressure. So I can immediately take out answer choice D. I'm left then with answer choices A and C. I need to figure out which one has the highest pressure and the lowest temperature. So this is going to take out answer choice C, and I'm left with answer choice A. How can I mathematically correct for gases at ideal behavior? I know that the ideal gas law tells me PV is equal to nRT. So how can I make corrections then to this equation to reflect those changes in ideality? And the answer to that question is what we call the van der Waals equation. This is an example of the van der Waals equation. We know that we have the ideal gas law here, that's PV equals nRT. The van der Waals equation is this guy. Notice that this correction here is how I can correct the pressure by adding on these known values of volume, and also this constant. A and B are both constants. And in this term, I can correct for the volume. Now, you are not required to know how to use this equation. This is just information for you to know how you can make a correction. So if I were to ask you, how can I make corrections to the ideal gas equation when I know that a gas is going to deviate from ideality? And your answer then is the van der Waals equation. We can also talk about the acidic properties of gases. So remember back from chemical reactions that if I take a nonmetallic oxide and throw that into water, that's going to produce an acid. And as an example, I want to talk about the synthesis reaction of carbon dioxide and water. So this is our example reaction. If I take carbon dioxide gas and throw that into liquid water, I'm going to produce carbonic acid. And remember from chemical reactions, we can think of carbonic acid as just an aqueous solution of carbon dioxide and water. And in that case, it's a reversible reaction, so we can draw a double reaction arrow to show the reversibility of this reaction. So that's the end of our gas laws. You now know about 8 to 9 different gas law equations and how to apply those. We've also talked about kinetic molecular theory and how gases can deviate from ideality. And we wrapped up here with stoichiometry and gases to show that this unit is theoretically very heavy and also very math heavy as well.